Good morning, everyone. Welcome to this PRAESENSA Automatic Volume Control webinar, talking about configuration and mounting guidelines for AVC. Here with me is Bas Beekman, Product Specialist and Application Design Engineer, and myself, Anton Thiele, in the same role. Today, the objectives are, as mentioned, providing design guidelines for automatic volume control in PRAESENSA. And the topics are a general introduction about AVC, about automatic volume control, then something more details about the ambient noise sensor we are using with PRAESENSA, then some basic acoustics for noise sensing in order to understand what would be the best placement. So this introduction 0.3.4.4, where we talk about the placement recommendations, and then something on AVC operating modes, configuration, and diagnose. Well, let's start. AVC, automatic volume control. Why would you need automatic volume control? Well, over time, the ambient noise levels in an area can change. So, for example, take an airport where you have a full arrival hall, or maybe in some quiet hours in the evening, you have an empty arrival hall, which makes a large difference in noise. Same in a factory where machines would be on or off, or on a railway platform where many people are waiting for a train or only a few are waiting. So in a sports stadium where people could be quiet or people are cheering and clapping. And as a result, depending on the ambient noise level, the announcement will be clearly audible, that's one, so very clearly audible, or it will be inaudible due to the high ambient noise level. So why then AVC? Yeah, to have a clear and intelligible announcement, despite of the background noise level. And how to achieve it? Yeah, for this we have the ambient noise sensor, the ANS, and the AVC, the automatic volume control function in PRAESENSA. AVC is then the algorithm in the system controller of PRAESENSA that can change the volume of an amplifier channel. So the AVC, the automatic volume control, responds to changes in the ambient noise level data in an area, which is then measured by this noise sensor. The ANS is the sensor that measures the ambient noise level in an area, and it sends the data to the system controller and the AVC algorithm, which is hosted in the system controller. So the AVC uses the data from the ANS, from the noise sensor, and changes the volume of the amplifier volume accordingly. So if the noise level goes up, yeah, then you could have an increased volume. Yeah? Until the max intelligibility is reached. If the noise level goes down, the volume goes down. And that would also mean that you have minimum annoyance in a quiet period. You don't want to have very loud announcements because that's then how it is perceived. Important is that AVC does not affect emergency priority calls. So in case the system is in an emergency condition, so when you have an evacuation message going on or an emergency message going on, then the calls are always at maximum volume. So at that moment, the ANS, the noise sensor, is not anymore part, and the AVC doesn't is not in operation anymore at that level. There's also a misconception about automatic volume control. That it would increase the volume when ambient noise level goes up, because there is a maximum to the volume that speakers can deliver. Yeah, and so the right approach is to think about AVC, which reduces the volume when ambient noise level goes down. So, and then the maximum volume, which you normally have available in your PA system, is reduced because you don't need to have that high volume. And that's the way how you should always think of when you are designing your AVC installation. So important, the overall system design must be capable of being louder than the maximum expected background noise level. And AVC, automatic volume control, reduces the call or music level when the ambient noise level goes down. Yeah, then there are some limitations. So the AVC cannot determine the difference between ambient noise and background music. And the AVC is not a magic tool to solve acoustical problems. There are many other aspects, and we come back to that later, which can influence the intelligibility. Yeah? Well, let's go then to the sensor, the ANS, PRAESensa PRAESENSA Ambient Noise Sensor. It monitors the changes in the ambient noise level in an area. Yeah, and it sends this ambient noise level data to the system controller. So it's not sending an analog audio line, how it is in more traditional systems. No, it's using an encrypted TLS encrypted control data. It will send to the controller only with the level data. So the advantage of this is that you have a very low network load, so you don't have any audio going over your network, and there is no eavesdropping possible. So if you would have analog microphones, yeah, then you could easily do eavesdropping. That's also impossible with this, and it's only control data. So the system controller then adjusts the output level of the involved amplifier channels, and that could be for both calls and for music. The AVC in PRAESENSA can handle up to 4 noise sensors in an area, in one zone. So you define in PRAESENSA zones, and zones consists of multiple amplifier output channels of different amplifiers, which cover a large area, for example. And you could have up to 4 noise sensors which operate together to cover a large area. The AVC uses the data from the ANS with the highest noise level. The fail-safe operation is then as follows. It's supervised by the system controller, and the failure or disconnection of an ambient noise sensor, that's a call volume automatically will go to max volume, and the BGM volume will remain at the last setting. Yeah, that's when an ambient noise sensor would be disconnected from the system. So it doesn't mean that everything is completely stopped. So the BGM will remain as it was, and call volume will automatically go to the max volume. Same as when the system would reach into an evacuation or emergency condition, then this is also ignored. That's the same approach. The noise sensor is powered by power over Ethernet, PoE. So you need to have a PoE port or a PoE sourced device to connect to this unit. Yeah. It is part of the certification of the EN 5416 and the ISO 7240. And this means that it can be used in combination with the evacuation system of PRAESENSA. Then goes to the next step. That is are the basic acoustics for noise sensing. And this is important later on to understand where you should position these sensors. So let's first have a look at the properties of sound. So when you would have a crowd somewhere in a room, for example, and you are listening at a distance, yeah, then you would hear direct sound which comes directly from this crowd and reaches you in person or your device, and without any reflections. So that's what we call direct sound, without any obstacles or something. But there is also reflected or diffused sound in an area, which means that is the sound which is reflected against the ceiling or the walls, and at the end that will also reach your ears, yeah, or your device. So that's direct sound and reflected sound. Well, the properties of direct sound differ from the reflected sound. So for the direct sound, that means when you look at the sound pressure level, that decreases when the distance of the sound source increases. So when the sound source is further away, your sound pressure goes down. So you have less sound. Yeah, that's I think pretty logic. For a sound source, for example, a standard ceiling or a cabinet loudspeaker, it can be calculated as follows. And that means that you have a decrease of 6 dB when doubling the distance. And in this diagram, you can see that as follows. When you have here at 1 meter a distance and sound pressure somewhere measured of 80 dB, then when the distance is doubled, the sound pressure is reduced with 6 dB, and you will keep 74 dB left here. And the same, for example, when you are then at 10 meters, yeah, then you already have a decrease of minus 20. Yeah, and at 100 meters, then it will be minus 40 dB. So with minus 6 dB when you double the distance. That's the property of direct sound, which you need to keep in mind. For diffuse sound, it's different because you have reflections which cause a reverberant or diffuse sound field. So it comes from all directions. And in an ideal room with even distribution of reflective and absorptive materials, the reverberant or diffuse sound field has more or less the same sound pressure level. So that's perceived as the same in the whole room because it's reflected at all sides. So you will there have everywhere about the same sound pressure. Another aspect which you should keep in mind when we further on going to calculate are the reflections which cause a reverberant or diffuse sound field. And this is there's a formula for that, and that's actually what's the important factor here is the reverberation time. So how long does it take before your sound is quiet again? And so we measure this with a sound source, which you then switch off, and then the time you measure until the diffuse sound pressure level is decreased by 60 dB. So from one point you stop the sound source and then wait until the sound is dropped until 60 dB, and that time, that's what we call the reverberation time, RT60. And these that's depending on the type of room, but also on the type of acoustic absorptive materials, etc. So you can, of course, influence that RT60, but that's pretty important for the for the way how the acoustics are in your room. So, for example, a classroom that would be about half a second. When you look at the concert hall, there you must have more reverberation time for a nice sound. But in the church, it goes maybe up to even 10 seconds, which then has a large influence in your intelligibility. So, but these are some RT60 examples. Yeah, when you look at sound propagation in free field, for example, open air festivals, yeah, there you don't have any diffuse sound, but there are no walls or ceilings. So there, this doesn't exist. The more reflections, the longer RT60. So then what is important now for this automatic volume control is also the combination of the direct and diffuse sound fields. So at the left side, you see there you have the direct sound pressure level, which decreases when the distance is doubled, and then for every double distance it goes minus 6 dB, as I mentioned before in my previous slide. But when you are then in the diffuse sound field, there the pressure is more or less constant. Yeah, so that's at a particular level. There, it doesn't decrease further. It's because of all the reflections, it stays constant and independent of the distance. Yeah. So when you then look at the total sound field in a room, the total sound pressure level decreases until you reach a critical distance where the sound pressure is not anymore further decreasing based on the distance. So beyond that critical distance, the total sound pressure level stays more or less constant. That's what you can see here with this green line. So at the left side from this critical distance, you have your direct sound field. On the right side of that critical distance, you have the diffuse sound field. Yeah. And then the total sound pressure level, that's then this green curve, which you somehow need to determine in your area where you want to install later on also your noise sensors. So we come now to this ambient noise sensor placement recommendations. And for that, I come back to that previous diagram. And so the ambient noise sensor should now be in the diffuse sound field. So not at the direct sound field, but in the diffuse sound field, meaning near to the noise, but not too close. Yeah, it depends on the room acoustics as well. So it's from the critical distance onwards, there you could then position your noise sensor. So away from the direct speakers, and especially when it is used also to adjust background music, you should be in the diffuse sound field, yeah, not in the direct sound field. Because yeah, music signal will be measured as ambient noise. Yeah, so that's something which you need to keep in mind. So also not too close to an air vent outlet or an airco, because if you are in that direct sound field of an airco, then yeah, this airflow will give false measurement data and also will influence and less lower your volume in that case. So also not too close to large machines. The noise level of large machines will be higher than the noise level in the rest of the room. So you need really to look at which are my sound sources, and stay away from the direct sound field of all these different sources there. Yeah. And yeah, but yeah, where is now this critical distance? There is a formula for that. Yeah, it depends on the following parameters. So that's the volume of the room. Then you have the reverberation time. And so, and this RT60 is of course also depending on acoustical characteristics of that room. And then you have your Q factor, so the directivity of the sound source. So, and diffuse or omnidirectional sound sources have a directivity of Q1. So that means that if your sound is going on all directions, then the factor is just 1. Yeah? And this leads to minimum distance to keep the noise sensor away from these sound sources. So that's this critical distance which you can calculate then. And the microphone of an ambient noise sensor is also omnidirectional. And yeah, for these RT60 parameters, there is a diagram which gives you some direction, like here, and that where you can see at the horizontal axis, there you see the volume of a room. So that's here at the horizontal axis, you see this volume of an area of a room, and then furthermore you have the reverberation time. That's the RT60, which is here from somehow 1 until 4, which you can select, and then the color indicates then the minimum distance to keep your noise sensor away from sound sources. Yeah, so that's then somehow a guideline for the position of your noise sensor. So for example, when you have a room of 2000 or 3000 here, you can see 2500 cubic meters, and you have a reverberation of 2.5 seconds. You're somewhere in that area from 2-3 meters. Yeah, so that's just something which could help you then in your position. But there are also some other factors which you need to keep in mind when you are for the speakers which are there for your direct sound sources. So these need to have an additional factor on the critical distance. So that's some rule of thumb that for ceiling speakers you need to calculate then 1.4 times the critical distance, which was shown in the previous table. And so you have that, yeah, for horns, loudspeakers, it's much more. It's because that are very directive devices, of course, and where it's even 5 till 6 times. Yeah, so this is really some basic guideline, but yeah, keep in mind here that these are the rule of thumb factors on top of what you just saw in the table to based on the volume on the RT60 to position your ambient noise sensor. Yeah, in areas with high ceilings, there suspend the noise sensor from the ceiling down to approximately 4 to 6 meters above the floor. And for large areas, use multiple sensors, so maximum 4 sensors per zone, as mentioned, and that you can use then to cover a large area. The sensor with the highest, which picks up the highest noise, is then your decision maker for the total volume in that area. For AVC and BGM, consider the directivity of loudspeakers and increase the distance to the ans if it is mounted in front of the loudspeaker. That's what we just mentioned. So increase the distance with these factors. Yeah, then also you might have some temporary noise sources. Consider the worst case of noise sources being active when choosing an ambient noise sensor mounting position. So also when you do the measurements, consider these worst case scenarios. Yeah, the critical distance. Yeah, so do it not place too close to individual sound sources in general, and not in the direct sound field, of course. And volume control of individual zones. Do not place the sensor too close to the edge of a zone. It might pick up noise from adjacent zones. That's also something which you need to keep in mind here. And consider discrete noise sources. Do not place a sensor near machines, heaters, ventilators, air conditioning, and in case are you going to use it outdoors, then again 4 to 6 meters above ground level, where the public is expected to be. AVC operating modes, configuration and diagnose. So now have a look a little bit more on how you then use this in PRAESENSA. How do you configure it? Yeah, we have 2 operating modes which you can use in PRAESENSA, and we can only use it for business calls with live speech and pre-recorded messages, and also for music. But when we use it for business calls, then you normally use the sample and hold feature. So that means your ambient noise is constantly measured. So that's the sampling phase. Also, if you don't make any live speech, you don't make any calls, then still the ambient noise is measured. Yeah. And call level is adapted to the actual noise level. And this AVC behavior can then be configured. When the call starts, the call level is fixed according to the last measured noise level. So before the call starts, you still have the latest sampled ambient noise level, and that is then used to adapt the call level. Yeah. So and then it keeps that at that level, so it doesn't adapt it anymore. Then you have your live speech coming out of the loudspeaker, that will not directly influence the ambient noise adaptation. Yeah. If the noise level changes during the call level does not change. So and that's to avoid volume runaway. And with that volume running way, I mean then that you think, or the system thinks, oh well, you have now a higher noise level, so I should less reduce my volume. So that's something which you want to avoid. Failure or disconnection of the ambient noise sensor, then the call volume will automatically go to the max volume. I mentioned that already before. So then this whole principle is ignored. So how does it then look like in a diagram? So you have a particular noise level, which might at some time increase, and you have a call level, which is continuously sampled and also then will follow the noise level. And then at some stage you are going to make a call, and that call is then based on the fact what was sampled before that call was started. When the noise level goes down again, the call level is reduced, and when you would make a new call, then the new sample will be taken as your next call level. So here you have, on this you have a higher level during the whole period. Even when the noise level is already went down, you can see that the call level still is on that higher level. Yeah, and here at the next call, when it is low, yeah, it remains low. Yeah? So, and it is adapted again to the new samples here. There are some parameters you can configure. So there is an ambient noise threshold, from where that the call level is being reduced. So that's the maximum noise level from where the call level is start to being reduced. Yeah, you have also an attenuation range, so you can have a maximum adaptation of 4 till 18 dB. You can set. So you can set maximum 18 dB attenuation of your call level, of your maximum call level. Then you have an attenuation slope. That means how quick your call level will be adapted based on what is sensed. Yeah. So that's the slope. Oh, sorry. The attenuation slope is the dB. How many dB is adapted and is attenuated for that. I mean the adaptation speed. That's what I meant here. How quick is the call level being adapted at the moment that the noise level increases. Yeah. So, and then that is your adaptation speed. Then you have the tracking mode that's used for BGM only, and the ambient noise in this case is measured constantly, so it is sampled, and the BGM level is continuously adapted to actual noise levels. So the AVC behavior can be configured, and the call will always overrule the music in that case. Yeah. So important now is to avoid this volume runaway. So your ambient noise sensor should be close to the noise source in that case. And a noise source in that case is not a loudspeaker, but the real noise source which you have. Because else that will pick up the call of the music and will adapt it. So you must check this and set the right parameters and distance of the noise sensor in that case. So it should be far away from the speakers. And in the diffuse, then the diffuse sound field is even more important, but to position it at that location. When the noise sensor would fail, that's the same again, but then the music volume will remain at the last setting. It will not be adapted, but it will, for this, it will keep that AVC set to the last one. So it's a slightly different behavior than for the sample and hold. Yeah, here this is then how it looks in the diagram. So you have your tracking mode, you have your noise level, music is continuously playing, and then your music level is might, in case of the noise, when the noise level goes up, might be slightly increased, and when it goes down, it might be slightly decreased again. Yeah. and it's continuously sampled in that case. So that's you have this threshold again from the location from where on the attenuation starts. You can set this between 50 and 90 dB again. And you have the attenuation range, how many dB of the level can be reduced in that case of the music. And you have your adaptation slope, and that's then how many dBs are attenuated based on the dBs the noise level is increasing or decreasing. Yeah. Then you have your adaptation speed, if you want to have it slowly responding or quickly responding, that you can set with this adaptation speed. Tracking mode. Well, then we come to the system configuration in PRAESENSA. So how do you configure it? Well, the ambient noise sensor is like any other device, a part of the system composition. So that means it's just like an amplifier or any other device. It is monitored and being supervised by the system. And it's so you can add it to the system composition, and you give it a name and a location maybe, and so it's recognized on the network, and you can just add it to your configuration. The configuration settings of the AVC, of the automatic volume control, is at the zone. So when you go to the zone options, there you have the settings of the zones. I will later on show it in a real system, so then maybe you can see it a little bit better. So you select the zone, and you can assign one or more ambient noise sensors, which are then a maximum 4, which can be assigned to that single zone. So the AVC uses data from the ANAs with the highest noise level. In that case, it will pick it up as important. An ambient noise can be assigned to one zone only. Always check for configuration errors in that case. You can not assign an ambient noise sensor to a zone group. It is assigned to a single zone. Yeah, so you must assign in that particular fact then the real zone to which has a number of amplifiers assigned, and that's where your ambient noise sensor is reflected. That's also mentioned here now. Enable AVC you need to do, and select control of BGM. That's the tracking mode. So when it dynamically will adapt the volume, or for the control of business calls, you can use then the sample and hold method. That's with the checkboxes at the lower right corner. Yeah, the ambient noise threshold, I showed it in the diagram. That's something which you can set between 50 and 90 dB from where the output is going to be attenuated. From starting from that ambient noise level, it's going to be attenuated to a lower volume in that case. So, and then you have the range from 4 until 18 dB in 1 dB steps. And they have the adaptation slope, so the rate of attenuation related to the ambient noise change. And so that means if you have you want to have a 1 dB attenuation, when you have a change of the ambient noise of 1 dB, then you set 1 to 1. If your ambient noise is changed for 2 dB and you only want to attenuate for 1 dB, then you have a 0.5 dB, which you only change then in that case. So you can here play a little bit with that range with the attenuation slope. The adaptation speed is how fast the AVC responds, and then that's what you can set. Furthermore, you have then the audio processing page, where you can where normally the standard A-weighting filter is used, which is based on the normal hearing, and you can change the EQ settings here, but make sure that you know what you're doing. So have here an acoustical expert to maybe adapt something of this EQ settings. For example, to filter out particular noise sources which you cannot avoid yeah, so that's something which you could tune here. Then there is a diagnostics page, and there you can have when you open the particular sensor, you can do a measurement, and there you can directly see the actual noise which is picked up by that sensor. So, and there you can also, when you keep in mind your attenuation range, your slope and speed, etc., you can there see the range and with all these parameters, you can see then how it is adapted. You can next compare the measured noise level with the sensor value. So you normally go with an SPL meter to the field, and where you then really measure your actual noise, and you could then calibrate that based on the sensor level which is picked up by the ambient noise. And with that, we have an offset parameter to adapt the noise level to the measured noise level source. Yeah, so that's something which can help you then to adapt the values to the actual sound pressure which you want to what you expect and what you measure there really. If you have low ambient noise level, check the AVC response. So see how it is then adapting, because you can also see then the adaptation in this diagnostics field. So you would then expect that it adapts. If it doesn't do this adaptation, then you might need to change something in your parameters. Yeah. And here at the right corner, you can then see the real adaptation which is happening when you would then use the noise sensor when you would make a call. Yeah, so what can you expect from AVC? If you have no AVC at all, then the call is a fixed level. So then nothing will change. So you just have a particular here, for example, a 90 dB SPL. A result being too loud in low noise moments. So there, when you have very low noise level, like shown here, then this is perceived as very loud if you have this 20 dB difference. Yeah, when the noise level goes up and it's only about 10 dB difference, that would be the ideal approach. When then the noise level goes up, yeah, then at some stage it becomes inaudible. Yeah? So so then you cannot do anything there. Then the call level is below the noise level, and you don't hear anything more. So you see an example of a very large noise level variation. So maybe you should think here about looking in your acoustics to at least to optimize something. But yeah, but this is when you don't have any AVC in place. Ideal AVC is where everywhere you have this 10 dB difference between the noise level and your call level. And that means that your speaker lineup and channel power should be able to reach the expected maximum call level. And that would be the ideal solution. Again, you would have here an yeah, but with the AVC range of 30 dB, you could reach quite a lot here, yeah, to reach this difference. AVC attenuation range equals the noise level variation here, and that would be then the ideal solution if you would have such a large range of difference in noise level. Yeah. PRAESENSA AVC is like a call level follows the noise level. So here you would have the ideal solution here now that everywhere you have this 10 dB until the maximum call level and where the noise level is adapted when you have this set. So noise level variation is below the 18 dB. So we have here 15 dB. So we can adapt it with the 15. And the AVC attenuation range adjustable between 4 and 18 dB to match the noise level variation. Yeah, ambient noise threshold is set to the maximum noise level in this case. Yeah. If you can see it, like you have the 80 dB of the ambient noise threshold, and with this adaptation, so you have your 65 dB of difference here. You have your maximum variation of 15 dB. System. So for high ambient noise level variations, when you would have really again this 30 dB, the system speaker design cannot handle the high ambient noise level. So you really go here until a very high call level, what you would expect if you want to be 10 dB above that high noise level. Yeah. So at the lower, it's possible, but there it would be maybe even perceived as very loud. But on the top, it's impossible to do that. So in this case, the possible solution is to change the speaker design and wait with the call until the ambient noise level is lower. That could also be an option. But yeah, you really must look also into other things. This is something which you cannot fix with AVC. Yeah, and even not when you would have an AVC function somewhere which has a higher AVC range, because at the end you would have a very loud call level, which is could even be dangerous. I'll come back to that later. High ambient noise level variation, so the speaker design could reach here up to 105 dB. And you could have the 18 dB range, which means that you have a maximum attenuation of 18 dB, and then you would have it up to a call level of 87 dB in that case. Yeah. And then at the left side, it can be the high level during the low ambient noise level that would be perceived as high, yeah, the 22 dB, but that's not something which you can avoid here. The noise level variation is here again this 30 dB. Determine what is the maximum expected noise level. By measurement, check tables with noise levels you can expect in certain environments. Yeah? Decide if you want the call level to be higher than the noise level. And this may result, or I mentioned before, in very high call level and an expensive amplifier and speaker design. So yeah, if you can see already in this diagram here, when you go in the red area, you can already have hearing damage at some stage already. At when you have a ride on the mower, that's 3 hours, where you go around that above that 90, around that 90 dB, which really can already give hear damage. And so as you can see here, it's really dangerous to go up to that higher level. So you cannot win this with a further higher speaker design. So too high call levels could be harmful. So you must do something on your noise in that case. System speaker design should be able to handle the necessary required power and SPL, but yeah, exposure. So it is important to decrease the noise level in that case. Yeah. But before we go to the question Q&A, I just want to slightly show you the diagram. Let me log in again. So when you look at the configuration of the zone, so you have in the zone option, you have this ambient noise sensor which you assign. I have only one in my system. I assign this one to this zone. Then I have my volume settings here. And there you have also a checkbox on automatic volume control. And here you have this threshold. I now only use it to control of business calls. I have an attenuation range, which you can select somewhere. I say you're about 12. And you have your adaptation slope. So how many compensation do you want for the ambient noise change? and the adaptation speed. Do you want 5 dB per second or 1 dB per second or only 0.2 dB per second? So that's something which you can adapt and adjust here. Yeah, when you go to the diagnose page, there is this ambient noise sensor. I can start measuring. When you look here, I'm now talking here. It is pretty loud, so there is now no reduction. When I would place my sensor a little bit away, now you can see that the volume is going down. And you saw the adaptation. Now I start talking again, and the volume is again loud. This is continuously measured, and only when you make the real call, then this volume will be immediately sent to the amplifiers related to the zone where you are going to make the call. So only at that moment the call is the volume is being reduced, yeah, for these particular zones. So this is basically how you can adapt and also adjust your settings. If you want to play, if you say, like here I have a sensor level of 67, but maybe my real noise is, or maybe I have with my NTE meter, I'm going to ear level where I want to measure somewhere the real noise which is perceived at the people, at the public, and then that will measure a slightly other type of noise than what is the sensor, which is 4 or 6 meters above. So then you can also use and do an offset here to adapt that to the sensor level which you measure in real. So you have really some tools here to adapt it.